Hello everybody. So you know the OGC Web Coverage Service. In this webinar, however, we are going to introduce the Web Coverage Processing Service to you, or WCPS. This is a high-level query language which allows for server-side filtering and processing of massive spatiotemporal datasets.
We are going to introduce you to the practical side of WCPS by showing you how convenient it can be to apply on-the-fly processing on your datasets using the query language defined by the standard.
My name is Peter Baumann. I'm editor of the WCPS standard.
And my name is Vlad Merticariu. I'm one of the Razdaman core developers.
So, as has been advertised earlier, Web Coverage Processing Service is something that we also want to present here in our series of webinars. This is about the introduction to see the basics of WCPS. So what is it all about? We want to see what simple WCPS queries look like, how we can filter and process data on the server, and, well, we also need to understand how, in the first place, send WCPS requests. What do we need to know for that? As always, a little bit of HTTP and XML comes handy. We should know what a coverage is, so the coverage implementation schema webinar is our friend here, and also it's meaningful to have some overview on the web coverage service. So at least the core, the WCS core, should be known. Good. So now that we have the ingredients, let's dive into it. WCPS, in a nutshell, is a query language. So it's a high-level declarative query language that is actually specifically crafted for spatiotemporal grid coverages. So you might call it datacubes. The WCPS syntax and semantics is defined as an OGC standard. Document number is 08-068R2. And that is adopted since 2010. It implements the code shipping paradigm that is prominent in big data. Whenever your big data are too large to be shipped or processing is so complex that you don't want to do it your own, then you don't fetch the data, but you send your request. In this case, a query. And that allows you for server-side filtering and processing pretty much in the style of SQL. One big feature that is important, in particular for big data, is that only exact results are sent over the network. You could call it what you get is what you need. So you don't have to download a lot of data to find out whether they are of interest at all. You don't have to download large data sets just to throw away a large part because you have to cut out what you are really interested in. Actually, the processing is done on the server, so you get exactly what you wanted to have. This leads not only to better service quality for the client, but also to better bandwidth utilization, hence it is faster. And as the semantics is explicit, the server actually can perform a lot of checks before execution. That includes security and privacy. It includes quota management. And you can do cost-based optimization and parallelization to do fast evaluation of such queries. So what does such a query look like? Let's look at the anatomy. Overall, it's an iteration. It's an iteration like a loop, so we indicate a list of coverages, that's the red part, and we bind a variable to it. That is like a loop iteration, where on each iteration the variable is bound to a particular coverage, and then the expression in the return clause is evaluated with that variable value. So what we do here actually is we iterate over 3 scenes, scene 1, 2, and 3, and we want to return the whole scene encoded in TIFF format. So the coverage result will be encoded and sent over. Note that such a query does not always have to return coverages. It also can be scalar results, like in the second example, where we inspect just one scene, a panchromatic one, and we want to return the average over all cells. The result here will be a single value, and that's going to be transmitted in ASCII. So, in summary, the result of such a request when evaluated is always a list, and it's a list of either coverages or scalars. Now, for those of you who are familiar with xQuery, You might be reminded of the syntax there with that for loop and the return statement. Well, it's semantically pretty similar to any other set-oriented query language. In this case, it is tentative that we have built it close to XQuery because actually we want to integrate it with XQuery to have integrated data and metadata retrieval. But that is something for WCPS 2.0. So that is not yet our topic for today. Rather, let's see what else we can do. So I mentioned filtering. How is that done? Well, we add a where clause, which is an optional filter predicate. And there, if the predicate is fulfilled, then the coverage is passed through to the result processing, that is to the return clause. If the predicate is not fulfilled, this iteration is simply stopped and the coverage is discarded before processing. So actually, such coverages are not processed and they do not leave the server. The filtering is completely done on server side. Next part. We already talked about it, but let's make it official. So any coverage that is delivered must be encoded in a suitable format. Therefore, we have the encode statement equipped with an identifier of the data format. In this case, we want to get our $s encoded as a TIFF file. Of course, the format must match the data. So four-dimensional climate datasets you cannot squeeze into a TIFF file. And the identification, as you may know from WCS, is by MIME type. The same principle is adopted here. So we have standardized identifiers for data formats. Good, that's the basics. So we know about how to establish an iteration over some coverages, how to filter, and how to process. So far, so good. But what operations do we have available? Let's see. We remember from WCS core that we had subsetting, trimming, and slicing. That is something useful. We want to have that here as well. What we would do is, when we provide two coordinates for an axis, then this means trimming. It's an interval that is defined by lower and upper bound. In the example below, we have a trimming on longitude and latitude, where we provide two boundary values. This axis actually is retained in the result, so longitude and latitude will be in the result coverage. When we do slicing, one coordinate is sufficient because that establishes the slice point on that axis. And subsequently, actually, this axis is removed from the result. In the example at the bottom, we do a slicing along time, and we use the ANSI date coordinate system here, the ANSI date axis. And as we slice a particular timestamp, actually the result coverage will not have a time axis, but only long lat. So effectively, we cut out a two-dimensional coverage from a three-dimensional one. And what about the axes that are not mentioned in the query at all? Well, those ones simply are retained in full extent. That would allow you, for example, to say at the bottom example, to do a slicing along that particular date. And if you don't indicate long and lat, you simply get everything available, the whole spatial extent of the coverage. So where do we get the axis names from? These actually are defined in the CRS. So if you look under the axis abbreviation, you will find lat and long. And for the novel time coordinate systems that are being established by OGC, you would find, for example, ANSI date or geological date or whatever. Good. So now we can do subsetting as in a WCS request, but now it's embedded in an expression. So, of course, we have much more flexibility now. Good. What next we want to do is we want to play with the pixel values. There is a principle behind that makes it quite simple. We all know operations on integers. Okay, now we have an integer valued image. We understand immediately if we have an addition of 2 pixels, we also can add 2 images. Of course, that means simply adding the 2 images pixel-wise. Or do the difference or log of an image or whatever. So you get the idea. Every operation that is available on cell types is also available on the coverages as a whole. And so we have a very convenient way of writing, for example, I.read, so access to a component, or i.red plus i.green. All of that can be written easily and will be processed in the server. We have an example here for band decomposition and composition. So $i.red extracts the red band. That's also such an operation that we know from an RGB component from a single pixel, and that is now done on the whole image. And band composition, we put together band 1, band 2, band 3, that's what we call it, and this is obtained from our coverage $S by taking blue, green and red band respectively. Good. This can be extended to really do band math. So to combine operations, and indeed in WCPS you will find arithmetic operations, trigonometric, exponential, Boolean and comparison operations, and as we have seen, pixel composition and decomposition. So we might, for example, go into a time series and just do a simple thresholding. In our $t variable, we have the time series, and we compare element-wise against the threshold value of 42, and the result will be a Boolean time series of the same extent, where for every cell we have a value of true or 1 when the predicate is fulfilled, or 0 or false whenever the predicate is not fulfilled, so when it's below or equal to the threshold. Actually, in this case, we may want to submit it as a CSV file, because this is a convenient way, for example, to do diagramming. Even more convenient would be JSON encoding, for example. Another convenient and common example is band arithmetics. The example listed here is NDVI thresholding, where we look into a Landsat scene and we do the difference of red and near infrared band over the sum of red and near infrared band. And then we do some thresholding to see where there is vegetation. That again gives us a Boolean image where we have black and white for no vegetation or vegetation respectively. What you see here in particular is we don't need explicit loops over the images. That's all implicit. And that has two consequences. Number one, nobody can submit nasty infinite loops. And number two, the server can inspect the cells in any sequence it wants. That doesn't necessarily mean line by line or row by row. Actually, we can do partitioning on the server and we can do a lot of things to optimize. But this just on the side. Here's a practical example where this could be used, what we have seen so far. Actually, this image in the background is a screenshot taken from a query that generates a 3D draping. So the imaging guys told us, did you know, when you use a PNG image and feed elevation values into the alpha channel, which is meant for transparency normally, then actually such an image can be immediately rendered by the client using WebGL and getting a 3D image that can be presented in the browser, and you can look at it, turn it, and so on. Fine, we said. This we can write as a WCPS query. And so we established something that looks into a Landsat scene and into a DEM and combines both by putting any kind of bands into the red, green and blue channel. So here, for example, band 4, band 3, band 2. We also do some subsetting to get out some values, which is symbolized here. For the elevation data, actually we first need to do a scaling so that it matches with the resolution, but then we can squeeze it into the alpha channel and out comes our PNG, which is shipped to the client. So that has been implemented, and that allows actually to nicely build clients that are visually interactive and that hide the query language. So the JavaScript client would generate such a query internally and ship it to the server, and the human user would never see that query. Okay, so much about the basics. That shows us how WCPS works on principle. Let's put this a little bit into context. First of all, implementation. Actually, the WCPS reference implementation, which is Rasterman, is an array database system underneath that implements exactly that semantics. To be frank, actually this approach of adding n-dimensional arrays to SQL has been the blueprint for establishing WCPS. Rasterman offers a query language interface, and WCPS spices it up with geosemantics. We have lots of client connectors here. You can invoke rasterman from within R, QGIS, etc. So from open source tools, but also from commercial tools like InVisia ChartLink or ArcGIS. Underneath, there is a scalable parallelized tile streaming architecture where we do a partitioning and then partitioned evaluation. That has been evaluated successfully on more than 100 terabyte sized databases, and queries have been distributed automatically over more than 1,000 parallel cloud nodes. And as you can see at the bottom, rasterman is quite well known on this planet already. And in particular, I'm proud to mention that in 2014, rasterman was the winner of the Big Data Challenge done by T-Systems, where the Copernicus Masters competition was seeking winners, was seeking best of breed on a variety of area. So we were the winners in the big data area. Now, WCPS. Doesn't that ring a bell? Yeah, right, there was something like WPS, Web Processing Service. How does that relate? Well, one main difference is that WCPS has the full semantics in the query, and that means it's fully machine understandable. So this string here can be generated by JavaScript, and it can be understood by the server, and they all will have the same understanding of it. Is that different with WPS? Sort of. If you look at such a process description of a typical WPS process, then you find an identifier which is buffer, and you find a title which says create a buffer around a polygon. Oh yes, and then there is an abstract saying create a buffer around a single polygon. And this is the full semantics description. There is nothing else that tells you how the buffer is created and what that actually means in terms of rounding, etc. All of that is just in the human readable description. So actually finding and binding automatically, so automatic orchestration, is difficult with WPS. And then there is something else which is, well, very much down to earth. This query string approach of WCPS is very flexible because users can ask any question at any time. No need to reconfigure the server or do anything on server side. You just can let users ask and play with the data. On WPS side, on the other hand, the functionality available is fixed by the service operator. Somebody must have installed that process, and only then it is available, and it's exactly this process which is available to the user. So there are two important differences between both. Why is that interesting, this semantic interoperability as opposed to the syntactic interoperability of WPS? Well, it is a basis for machine-to-machine communication. As I said, visual clients and other services can compose requests automatically, and they can be sure that it always has the same semantics. And this actually can lead to interesting exchange between client and server. So, for example, the client looks around. Let's see, which server can handle reprojection and exponentials? Maybe some server does not support advanced math, so I have to find one that can do it for me. Or a server in the cloud says, okay, here is a sub-expression in the query, which I better pass on to node X because this node holds the data needed for it. A server might say, okay, evaluating this query will take about 3.5 minutes and over 500 objects match. So the client gets a better feeling for what is coming up. Maybe inadvertently the client requested too many data. And that may even lead to quota, where the server says, so sorry, this request complexity actually exceeds your CPU quota. Okay, that said, actually, don't interpret this as these are competing standards. Actually, they are complementary, and WCS and WCPS requests can piggyback a WPS, for example, for asynchronous processing. So, in the end, actually, we obtain a spectrum of standards where service providers can pick. So you can go for the data-intensive part and offer WCS for data access with fixed request types. You can, on the other hand, establish processing with predefined processes using WPS. And in the middle, we have WCPS, which allows ad hoc analytics. Everything you can write down in an expression can be evaluated by the server in a flexible way. So these overlap, these can be mixed, and service providers, again, can pick whatever is most convenient in their particular ecosystem. Now enough about theory, let's go practical. Vlad will show us a couple of examples how to work with WCPS.
Hi, we're now going to look at some hands-on examples of WCPS. First of all, let me show you the datasets that we will be using during this session. If we open the WCS client, from the list of available coverages in the capabilities document, we will be using the following. Multiband is a 2D coverage representing a USGS satellite image of northern Germany, which extends on easting from 200,034,989 meters to 500,467 meters, and on northing from 5,816,800 meters to 6,097,439 meters. Multiband small is another 2D coverage constructed out of a subset of the original multiband coverage. And average land temp is a 3D data cube containing the average monthly temperatures during the day over time. Its extents are on latitude from -90 to 90 and on longitude from -180 to 180, so it has global coverage. And in time there is a slice for every month starting February 2000 and ending June 2015. Now that we know the datasets, how can we issue a WCPS request? The recommended way is through the processing extension of WCS. Assuming that Trustdaman is installed and running, by default you can access the WCS service at localhost 8080/Trustdaman/OWS, and the process coverages request looks like this. The service is WCS. The version is 2.0.1. The request is process coverages, and the query specifies the WCPS query that you want to execute. In this case, the query returns the scalar value 1. So if you have a client accessing data through WCPS, here is where you want your client to send the requests. Alternatively, for testing purposes during development, you can use the specifically designed tab in the WCS client called Process Coverages. This offers you a visual interface to type the queries and execute them, and also has some visualization capabilities for 1D and 2D data, which can be activated by specifying the keywords diagram or image in front of your queries. So if I type in the same query here for C in average length temp, return 1, and click execute, I'm going to obtain the same result. For this webinar, we will be using the Process Coverages tab of the WCS client to issue our WCPS queries. As seen earlier, a WCPS query has two mandatory clauses. A for clause that defines iterators over the datasets that you want to access, and a return clause that defines the result that you want to obtain. Optionally, a where clause can be used for server-side filtering of unwanted results. The result, unless it is a single scalar value, must be encoded in one of the supported formats, such as CSV for 1D data, PNG, TIFF, JP2 for 2D data, NetCDF for 2D or more, and so on. So if I wanted to find out the average of the multiband small coverage, I don't need to encode the result as it is a single scalar value. And I can do that by typing for C in multiband small, return average of C. If I click execute, I'm going to see the result band by band, as this coverage has 3 bands, without the need to encode it. If I want to retrieve the multiband small coverage, I need to provide an encoding. Since this is 2D, let's say that I wanted PNG. I can do that by typing in the return clause, return encode of C and PNG. Because this would return an image, I can tell my client to display it as such by specifying the image keyword in front of the query. So I can type here image and click execute, and now I'm going to see how the coverage looks like. Now let's see how we can subset coverages. A 3D to 2D subset would be, for example, selecting the average temperature in July 2005 from my temperatures dataset, which was called average length temp. Subsetting is done via the brackets operator, and I don't specify anything on the first and second dimensions, which were latitude and longitude, so that the full extent is provided, and I specify a single point in time, which was 2005 July, so that the dimensionality is reduced from 2D to 2D. As this is 2D, I can request it encoded as PNG and display it as image. Displaying temperature values directly as pixel values may not be very visually appealing, and we will see in the advanced WCPS session what further processing we can apply to generate, for example, a color map on the fly. Further, a 3D to 1D subset would be, for example, selecting the temperature in Bremen over 2010. To do that, I must fix the latitude and longitude to the ones corresponding to Bremen. The latitude is 53.08 degrees and the longitude is 8.8. And on the time axis, instead of specifying a single point, I specify an interval. So 2010 January until 2010 December. Because this is 1D, I requested encoded as CSV. And I see the list of temperatures corresponding to the monthly averages during 2010 in Bremen. As I said, the client supports visualizing 1D data as well as diagrams, and I can do that by specifying the diagram keyword in front of my query. And I can visualize the same set of values, but this time on a graph. Selecting a single value can be done by fixing points on each of the 3 dimensions. So for example here, instead of specifying an interval, I specify just August 2005. And I find out that the average temperature during the day in Bremen in August 2005 was 18.81 degrees Celsius. Now let's look at how we can actually process the data. If we come back to the example with the average temperatures in Bremen in 2010, so 2010 first until 2010-12, these are displayed in degrees Celsius. Let's say that we wanted to display them in Kelvin. To do that, we would simply add 273.15 at the values. And if we wanted, say, in degrees Fahrenheit, we would add 32 and multiply the Celsius values by 1.8, and we would obtain them in degrees Fahrenheit. Besides the mathematical operations, there is a set of predefined summarization functions available, such as min, max, average, count, and so on. So for example, if we wanted to find out the minimum of the values of the average temperatures, we could do so using the min function. Conversely, the maximum would be given by the max function. The average of the 12 values would be given by the average function, And if we wanted to answer questions such as in how many months the average temperature in Bremen in 2010 has been more than 15 degrees, we can do so by using the count function, which takes as argument a binary coverage, that is a coverage containing only zeros and ones, which we obtain by writing C subset more than 15. This gives us a coverage containing ones for the months that respect the condition and 0 for the ones that don't, and count tells us how many of the values are ones, and we find out that in 6 months in 2010 the average temperature during the day was more than 15 degrees. Now let's look at the other dataset and see some band operations. As I mentioned, multiband is a free band two-dimensional satellite image. And to see how it looks like, we can do a simple subset. So we can write for C in multiband, return encode of C. On easting, let's say that we go from 300,000 to 330,000, and on northing from 5,820,000 until 5,850,000, and we show the result as a PNG, display it in the client as an image. This is how the subset that we have selected looks like, and it has 3 bands corresponding to red, green and blue. We can see the names of the actual bands by going into the capabilities tab and clicking on the multiband coverage, and in the describe coverage tab we see that the first band or channel is called red, the second one is called green, and the third one is called blue. Now if we wanted to select just the first band, we can call here c.red, and we will see the values only of the first channel. We can do the same by, if we don't know the names of the bands, we can do the same by calling c.0, so the index of the band, and we would obtain the same result. So for the second band it would be c.1, which would be the same as c.green, and for the third band it would be c.2, which would be the same as c.blue. If we wanted to do a band recombination, so let's say that we wanted to invert the order of the bands and see how the image looks like, we can use an operator called range constructor. It looks like this. It's a set of curly braces, and inside you can specify each band and each band name and the formula for how the pixels are computed. So let's say that we wanted 3 bands. The first one is red, and for the red we want actually to put c.green. For the second band we want it to be named green, and for the values we want the values from the blue channel, and the third one we want it named blue, and for values we want the values of the red channel. So we obtain an image which is similar to the first one, but has the colors inverted. Now let's say that, for example, we wanted to keep the original image, so c.red, c.green, c.blue. This looks like the original image, but instead we want to use in the green channel the minimum value, so let's say 0. Now if I fire this query, if I click execute, it's gonna complain about the types, because in a free band type, this is a free band image having unsigned char as type on each band, and 0 here doesn't have an explicit type. So I would have to do a cast. I can do a cast by specifying the type in parentheses. So I'm specifying that this 0 is actually an unsigned char to be a true RGB. And this is how my image looks like if I use 0 for every pixel on the green channel and keep the red and the blue bands as they are initially. Finally, let's do a band ratio, as it happens when computing the NDVI, for example, on a hyperspectral image, which can be done as follows. As I said, selecting the band with the index can be done as like this, C.0 minus C.1. So this is the difference between the first two bands over the sum of the first two bands. And I want to see when these pixels are more than 1. And if I execute this, I'm getting an image like this. If this was indeed a hyperspectral image, this would show me where there is more chances of vegetation being present in the picture. So that's pretty much it. Using these operations, you can already do a lot of processing through WCPS. Thank you for your attention, and if you want to see more, I invite you to watch the second WCPS webinar session, where we're going to explore a few more advanced operations.
And that was it for today. So we have seen about WCPS, this four-letter word which stands for a query language that allows filtering and processing of spatiotemporal coverages, using a process coverages request, which allows us to submit a query. We have seen about subsetting, pixel-wise processing, summarization, filtering. And if now this has brought you into appetite, then actually why not proceed to the WCPS Advanced webinar, which fits nicely with this one. For now, thanks for bearing with us, and bye-bye.